Hello everyone. In previous videos, we have seen the Markowitz's model for portfolio optimization. Markowitz's model is a full covariance model. But there is one problem with it, and that is that the number of data inputs that we need for implementing the model is huge. Specifically speaking, we are going to need n times n minus 1 over 2 data estimates to implement the model. So let us say if we had a portfolio of 50 securities, that would mean that we would need 50 times 49 over 2, and this is going to give us a huge number of data estimates required, 1225. This greatly increases our chance of making an error. The single index model, which we are going to talk about in this video, reduces the number of data inputs required, which is going to make it easier for security analysts. But this ease is going to come at a cost, and the cost is that we are going to have to sacrifice some accuracy. We are going to see that shortly. To begin with, let us assume a security I. If we want to write the return that we obtain from security I, we can say that the return from security I could be a sum total of two components, one of which is expected and the other one is the unexpected surprise element. So we can say that the return could be classified into the expected part, ERI, plus the unexpected part, which we can write as E of I. This E of I here is assumed to have a zero mean. And if we want to write its standard deviation, we can simply write it as a sigma. Let us now bring a common macroeconomic factor into the picture. Let's call that factor M. This common macroeconomic factor is going to cause a change in the returns of all securities in the universe. This means that the unexpected part of the return can be divided into further two parts. One is M, which is the macro factor, and the other is E, as we wrote here, which is firm specific. This is going to change our definition of return slightly. We are going to have to write our return Ri as being equal to expected return on security I plus the return that is associated with the common macroeconomic factor, and then the return that is associated with the firm specific factor. So M is a measure of unexpected macro surprises. We have said that before. And these surprises are going to average out to zero over time. And if we want to write the standard deviation for this, we can simply write it as sigma M. EI, which is this, as we said before, is unique to a firm. This means that M and EI are not going to be correlated with each other. So we can say that they are uncorrelated. Let us now look at the other part of the picture, the risk. If we measure risk as the variance of return, then it is easy to see that the variance is going to arise from two uncorrelated sources that we have just seen, this one here and this one here. So M, which affects all securities across the board, so that therefore we can call it the systematic factor, and E of I, which is firm specific and therefore can be called unsystematic. So if we want to write the variance of returns for security I, we could simply say that it is equal to the variance that is coming from the common factor, common macroeconomic factor, and the variance that is coming from the firm specific factor. It is also important to keep in mind that since M is the common factor, it is going to be correlated with all securities. E, on the other hand, is assumed to be uncorrelated across firms because it is firm specific. Let us now introduce another measure of risk into the picture, the covariance. So if there are two securities I and J, what is going to be the covariance between their returns? It is easy to see that the covariance is going to arise from the uncertain part of the return only, which is going to be for security I, M plus EI, and for security J, M plus EJ. So what we can do is that we can write the covariance between I and J as this. But because we have assumed that E's are uncorrelated across firms, they can be ignored. So this E is going to drop out of the picture, and this E is also going to drop out of the picture, which means that covariance between I and J is going to be simply this. And that means that this is equal to nothing but variance of the common macroeconomic factor. It is also reasonable to believe that though the returns of all securities are affected by a common factor M, not all securities respond to this factor in the same magnitude and same direction. Some are going to respond more, while others are going to respond less. Also, some are going to respond positively, while others are going to respond negatively. We can capture this sensitivity by writing a sensitivity coefficient for M, and we can call this sensitivity coefficient as beta. Once we do this, we can rewrite the single factor model by incorporating the beta. So Ri is going to be equal to expected return on I plus beta I times M plus EI. This becomes our single factor model. So let me write it here. If we want to write the variance of returns for I, we are going to again incorporate the beta into this expression. So we are going to write beta of security I squared times variance of M plus variance of the residual. This term here captures the systematic risk of the security, and this term here captures the unsystematic risk. We could also call this the residual variance, and we could also call this the firm specific risk. What about the covariance? The covariance is also going to change a little bit. So if there are two securities I and J, we can say that the covariance amongst their returns is going to be now, this is where I'm incorporating the beta IM plus EI and beta JM for the second security plus EJ. EI and EJ are going to drop out of the picture as before because we have assumed them to be uncorrelated. So what is going to be the covariance between I and J now? As a side note, let me remind you of one fundamental understanding about calculating covariance. Let me write it here. That if we want to calculate the covariance between AX and BY, where A and B are coefficients of X and Y, we could simply write this as A times B times covariance between X and Y. And we can apply the same understanding in this case as well. The coefficient is beta I here and beta J here. So we can write the covariance as beta I times beta J times covariance between M and M, which gives us beta I times beta J times variance of M. We can now give a contextual name. I always have a problem pronouncing this word, contextual. So I was saying we can give now a contextual name to our common macroeconomic factor M. We can call it the market, and a market index like S&P 500 can be used as a proxy. The moment we do that, we can move from the single factor model to the single index model, because we have now called the common factor the index. The single index model is simply arrived at by regressing the excess market returns on excess security returns. So let us write that here. Let us say that the excess return on a security I is equal to capital R I, and let us also say that the excess return on our market can be written as capital R with a capital M as the subscript. So if we want to estimate now the single index model at time period T, we can write this, that the excess return on security I in time period T is equal to the intercept, which we call alpha I, plus the slope, which is beta I, times the excess return on the market at time period T, plus the error term. What does it mean in our context here? This alpha I is the intercept, and it gives us the excess returns when market return is 0. Well, if market return here is 0, then this whole term is going to be 0, and our return on security I is going to be just equal to the alpha. What about the slope? This beta I here. This gives us, as we saw before, the sensitivity coefficient, and it measures the systematic part of the risk. This here is the error term. We can call it the residual. This residual is going to have a 0 mean, and it's going to represent the firm specific surprise element. An important question arises now, which is that whether a positive value of alpha is good for us or not. The answer is obvious. Since alpha is a non-market premium and represents an addition to the overall return over and above the market related premium, which is this, we are going to love it. If a security is underpriced, we are going to see a positive alpha for it. That is why we want to buy underpriced securities. we are hoping for a lucrative return from them. Security analysts and fund managers are always on the hunt for a positive alpha. So they are looking for positive alpha securities all the time. Sometimes they are going to succeed in their research. At others, they are not going to do so well. In recent times, we have seen that many fund managers who have been looking for positive alphas have not been able to outperform the market. You will also appreciate that somebody's gain in the market will also mean somebody else's loss. Therefore, if one party gains from a positive alpha, someone else is going to lose. As a result, the sum total of the alpha in the market is zero. So you have to remember this. So if someone is asking you what is the alpha of the market, your answer is that alpha of the market is competed away and it is equal to zero. Let us now spend a few moments on the other side of the coin as well, which is risk. We want to write the variance of security I. So from before, we have seen that this is equal to beta I squared times the variance of M plus the variance of the residual term. What about the covariance? If there are two securities I and J and we want to write their covariance, this is going to be equal to, let us see, we wrote the covariance a little while ago. This was it here. Let me highlight it in red here for you. Beta I times beta J times the covariance between M and M. And the covariance between M and N is nothing but the variance of M. So here also we are going to write the same thing. Beta I times beta J times variance of M, capital M. We have seen this earlier. What we need to do now is also to introduce another element into the picture, and that is the correlation coefficient between the returns of the two securities. The correlation coefficient, we know, is going to scale the covariance between -1 and +1 and is therefore more intuitive to interpret. We know that in the single index model framework, all securities are correlated with the market. Therefore, we can write the correlation coefficient between the returns of securities I and J simply as the product of the correlation of security I's return with the market and the correlation coefficient between security J's return with the market return. Now what do we know about this item here, correlation between I and M? We know that correlation between the returns of two assets can be written as this: covariance between their returns divided by a product of their standard deviations, the standard deviations of returns. What about this? What do we know about the covariance between I and M? We wrote the covariance between the returns of I and J here. So we can take a clue. What do we have here? We don't have an I and J, rather we have an I and M. So what is going to be the covariance between I and M? It's going to be beta I times beta M times the variance of M. We know by definition that beta M is equal to 1. Therefore, the covariance between I and M is going to be simply equal to the product of beta of I and variance of M. If we can say this about security I, we can say the same thing about security J as well. we can say that the correlation between the returns of security J, I should have written here covariance. So let me just scratch this out here and write here covariance between the returns of security J and the market return is going to be equal to beta of J times the variance of the market. Once we know these definitions, we can find out very easily the covariance of the correlation between the returns of security I and security J, which we said before is equal to the product, this product here. So what is correlation between the return of I and M? Correlation is this item here, but covariance is this. So we can write here the covariance of returns between I and M, which is beta I times variance of M, divided by the product of the standard deviations of their returns, multiplied by, we can write the same thing for security J. We can combine this and write it as a single term, beta I times variance of M times beta J times variance of M, all divided by standard deviation of I times standard deviation of M times standard deviation of J times standard deviation of M. Let us now return to the question of how many data estimates we are going to need for implementing the single index model. Let us see what we need. If there are n securities in our portfolio, we are going to need n estimates for alpha. We are also going to need n estimates for beta. We are going to need also n estimates of the residual variance. We are going to need one estimate for the excess market return, and we are going to need one estimate for the variance of market returns. So what is the total that we need? Let's add them up. N plus n plus n, 3n, and plus 2. So these are the number of data inputs that we need. So if we had a 50 security portfolio, what would be our data requirements? How many data points we would need? We would simply need 3 times 50 plus 2, which is going to be 150 plus 2, or 152 estimates, as against the 1225 estimates needed with the full covariance model. We saw that in the beginning of this video. Well, this looks good, isn't it? It is easier, and therefore there is less chance of making errors with lesser estimates. But this simplification, as I mentioned in the beginning, is going to come at a cost. Number one, in the real world, it is going to be difficult to classify uncertainty into macro and micro factors neatly. We have also assumed that E, which is our residual, is uncorrelated across firms. This may not be typically true, especially for firms which come from the same industry, because they may have some similar industry factors affecting all of them. So what is going to be the problem? If the residuals of two firms, for example, are positively correlated, we should not combine such firms together in a portfolio, because if we do so, we are going to simply increase the unsystematic risk. If we use the Markowitz's algorithm, the full covariance model, it is going to place lesser weights on such securities. But the single index model, which assumes that E is uncorrelated across firms, is going to simply ignore this fact. So what is the result? If we make a portfolio, if we combine such firms into a portfolio, we are going to have more portfolio variance, because some unsystematic risk is going to enter the picture. Likewise, if the residuals were negatively correlated, we should have higher portfolio weights for them. But the single index model won't make such an allowance. What does that mean? It means that we are sacrificing some diversification benefits, and we are going to have a below par diversification and therefore a suboptimal portfolio. Let us conclude this discussion now. Should we or should we not use the single index model? We have seen that index model is not as accurate as the Markowitz's model, but it seems a little bit practical as it can save some time. It can also save some work, a lot of work in fact, and also the likelihood of making errors. So if we interpret the results using our judgment, it can be helpful. It can be a valuable tool in portfolio management if we are also using our brains alongside the numbers that we are seeing from the regression model basically. In a later video, we are going to take some data and work with it in Excel to implement and interpret the single index model. For now, it's bye-bye. See you later.